Dr. Jaime Grunlan is the Leland T. Jordan 29 Chair of Mechanical Engineering at Texas A&M University, where he has worked for more than 20 years. He holds joint appointments in the Department of Materials Science and Engineering and the Department of Chemistry. His research focuses on thermal and transport properties of polymer nanocomposites. He's a world leader in organic thermoelectric materials, super gas barrier layers, and environmentally benign flame retardant nanocoatings. He holds 16 issued US patents and several EU patents, and he has published more than 200 journal papers with more than 26,000 citations. Dr. Grunlan has graduated 29 PhD students and has mentored more than 50 undergraduate students in his research laboratory. His work has been highlighted in the Smithsonian Magazine, Nature, and the New York Times. He is an editor of the Journal of Materials Science and he is an editor of the Journal of Materials Science and Progress in Organic Coatings and associate editor of Green Materials. In 2018, Professor Grunlan became a fellow of the American Society of Mechanical Engineers and was awarded an honorary doctorate from the University of South Brittany in France. In 2019, he became a senior member of the National Academy of Inventors. In 2023, he became a fellow of the American Chemical Society, and in 2024, he became a fellow of the American Chemical Society Division of Polymeric Materials Science and Engineering. And without further ado, I will pass it over to Dr. Grunlan.
Thank you. Yeah, it's great to be here. I didn't know about the Greater Houston section of ACS, but I guess I should have imagined that there was one. So anyway, yeah, I'm a coatings guy. I'm a polymer scientist, and so what I'll talk to you about this evening is the polyelectrolyte based protective coatings, as you can see in the title there. I figured I might as well make a little plug. I don't know if some of the audience maybe graduated from A&M, I'm not sure, but it's a big university not too far from Houston, in College Station, Texas. You can see some of the numbers and statistics there. I'm actually in the College of Engineering, even though I have a joint appointment in the Department of Chemistry. And so you can see in this international ranking, I think this is the College of Engineering that they rank number 10 in the world. And just this last year, the U.S. News put us as number 10 in the nation. And I've been 20 years at A&M. I think this is the highest ranking that engineering's ever had, maybe ever, but certainly in the last 20 years. So we're excited about that. So that's the bragging part of the seminar for Texas A&M University. My own research group, I'm very applied. So I used to, in the old days, always kind of frame all of my work in terms of properties that we wanted to achieve. But we're achieving these properties with polymeric materials. And so you can see flame retardancy, gas barrier, thermoelectric. There are, nowadays, I want to be a little more scientific. So I'm always pointing out that we do have these scientific pillars, I call it, underpinning everything that we're doing. So almost everything I do is some type of polyelectrolyte complexation. And there's a lot of polymer nanoparticle interactions that you'll see. Almost all the processing is water-based. And more recently, we're doing a lot of work with kind of, it's hot to say green chemistry or sustainable, et cetera, or renewable, but we are doing a lot of work with, more recently, with some naturally occurring polymers like chitosan and alginate and some other ones that are good for some of these properties that we are after. Every semester, I try to take a new picture of my research group. So this picture is probably only 2 or 3 weeks, 4 weeks maybe old. So that's the current research group. That's probably half undergraduate students and half PhD students, and I have a lot of international collaborations with good people, and I have a lot of good funding sources. Even though you'd think in engineering it would be the most common situation, most of my research funding is actually from industrial sponsors. We really are usually working on projects moving towards a real life product. So you can keep that in the back of your mind as I'm moving through things. Tonight, I just want to I'll tell you about the work we're doing in heat shielding. I'll give you a little bit of a background on polyelectrolyte complexes for people that are not super familiar. And then heat shielding will move into flame retardant and then move into gas barrier. I think I threw in a little thing about high voltage insulation as well that we do with, that's a new topic for me. But I usually use two different techniques to make a functional film or coating. One of the techniques that I'm not doing as often, just because it's too many processing steps, but you can make some really beautiful, high performance, functional thin films using this technique called layer by layer assembly. You're seeing it on the screen there, this cartoon, where I'm exposing a substrate to cationic and anionic nanoparticles and or polymers. And this is just one example. And this cartoon you're seeing here is supposed to be some kind of cationic polymer and anionic clay nanoplatelets. I call it a nano brick wall. And I have a lot of, we've done a lot of work on the nano brick wall kind of structure. But the beauty of this technique is it's self-limiting thickness of layers, and all the processing is done under ambient condition, and you can truly tailor just about everything in these kinds of thin films. And so a real life nano brick wall is on the screen now, and it's a 40 polymer clay bilayer film. Bilayer means one polymer and one clay layer paired together, anion and cation. And you can see that it's only 135 nanometers thick, even though it's 80 layers. So they're just 1 or 2 or 3 nanometer thick layers. It's basically monolayers of clay and monolayers of polymer. And it makes this tortuous path for gas molecules. So it becomes a very high gas barrier. But as I mentioned, it's very thin. You can play some games. I'm showing you immediately a trick we do to make thicker layers faster. And here, in this case, I'm using chitosan as my cationic polymer, and I'm using vermiculite clay as my anionic nanoparticle or nanoplatelet. Vermiculite has a 2000 aspect ratio, 1 nanometer thick plate that's on average 2000 nanometers in diameter. But when I put this trisma base, or sometimes we just call it tris buffer, into my chitosan solution, and I also put it into my rinsing solutions, it causes a thickening of the clay as it deposits, because there's some kind of a complexation that happens as you're depositing the clay. And so now you can see 6 and 8 bilayers of growth are more than 4. At 8 bilayers, I'm more than 4 microns thick. So I've kind of engineered a little trick to get much thicker film much faster. And so then as I'm monitoring oxygen transmission rate, so if you think about food packaging or protection of even organic electronics from oxygen, you need gas barriers for these kinds of things. And at 6 bilayers, I'm getting very close to an undetectable oxygen transmission rate, which means undetectable for me is below 0.005 cubic centimeter per meter squared per day, because that's I use this MOCON. They're not paying me, so I'm not advertising, but that's the tool that's in the food industry. People know this this Amatec MOCON tool that you can measure permeation with. This same coating I can deposit onto a 3 millimeter thick polystyrene plate. Think of this as IKEA furniture, mimic, you could say. And so a polystyrene plate with no coating on it is, of course, very flammable. So this is a little household butane torch that we bought at Home Depot. And then we have that 4 micron thick 8 bilayer clay polymer coating, the chitosan with vermiculite. And you can hold a torch on there for 15 minutes and you won't ignite that polystyrene plate. We can debate whether that means it's flame retardant or if it's just heat shielding. But, and so with that heat shielding idea in mind, we decided to take this, to look more deeply into this kind of a coating. right now in the world, when people talk about thermal barrier coatings, they're usually either talking about a very fancy ceramic coating, very exotic. GE on turbine blades puts these very exotic ceramics to protect them from high heat so that the metal doesn't weaken or distort. Another kind of heat shielding coating, you can see the second bullet point there is an intumescent coating. That's a one-time use coating that bubbles up. They usually put that on steel girders in a skyscraper, for example. When there's a fire, it'll puff out and thermally insulate the steel. We wanted to make this nano brick wall version of a heat shielding coating, and I kind of call this the poor man's hypersonic coating. There's currently a ton of research in the world on coatings for hypersonic aircraft of various types, because when you go Mach 10, the skin of something is going to heat up to 1200, 1500, 2000 degrees Celsius. And then that means that the actual metal or composite or whatever the aircraft is made of is going to be destroyed en route to wherever it's going. So we took this vermiculite, and in this case, we're using polyethylenimine instead of chitosan. But I'm doing this same thick growing layer by layer system with this tris buffer. Sometimes because of its full name, which you can read there, that aminomethane, we call it THAM, T-H-A-M, or tris. So don't be confused if I'm jumping back and forth. But this shows the schematic process of how we now put this nano brick wall. In this case, now I'm depositing that nano brick wall onto a carbon fiber reinforced composite, like an aircraft kind of composite that they're making Boeing aircraft with, for example. So this is just a model epoxy, carbon fiber filled epoxy composite system. And so what we did was we actually had a torch on a dog bone of this carbon fiber composite, and then we were measuring a stress strain curve in tension while we had that flame on the composite. And you can see it in the uncoated. These are post-burning SEM images, and so you can see the uncoated composite. You can imagine most of the epoxy is fully gone, and you can see the fibers are all splayed out. And if we zoom in, you can see that you can tell that they're not sticking together anymore. But the bulk of the composite that was coated with this sometimes 4 micron, we went up to 15, 20 microns of coating. But in any event, this quite thick, I think somebody forgot to mute their, but yeah, you can see here that we've maintained we've protected the epoxy that's holding the carbon fibers together with that coating. And FTIR can be used to prove that the epoxy is still there in the coated composite while it appears to be gone in the uncoated. And so this is the stress. This is where we're measuring stress as a function of time with a torch on a composite. And of course, the uncoated, and then 6 bilayer, 10 bilayer, 15 bilayer means how many bilayers of that nano brick wall we put onto the composite. And in any event, you can see that the stress level that the composite can hold dramatically, it reduces much faster without the coating. So we're buying time with this relatively inexpensive clay nano brick wall coating. With this XPS technique, X-ray photoelectron spectroscopy, I can get the oxygen to carbon ratio, and so that shows me how much oxidation is happening. And once again, if it's an uncoated composite, after that torch is touching it, there's a dramatic increase in the OC ratios because there's thermal oxidative degradation happening, but we don't see any evidence of that in the coated composite sample. So it's evidence of protecting that composite from the heat of the flame. But that's heat shielding, not flame retardancy. And so I always say if there wasn't COVID, I'm biased, but if there wasn't COVID, if COVID wasn't the big story the last 3 or 4 years, fire would have been the big story. even during COVID, there were major forest fires. I collect wine. There was Napa Valley had horrible fires. The wine region in Australia had horrible fires. Notre Dame caught fire. There was this Grenfell Tower. You can see a picture of it there in London. It was a true towering inferno. So even today in modern times, fire is a major force that has to be dealt with somehow, and we need to protect certain things from fire. There's certainly a lot of concern, and so there was a whole issue 10, 12 years ago. Chemical and Engineering News made it their cover story, and they talked about all the pros and cons of flame retardants and toxicity and the need for more environmentally friendly flame retardancy. And it was just at that time where my group was starting to really get into this topic, and they highlighted the use of layer by layer assembly at that time as a method for possibly making safer, very effective flame retardancy. And so we published a nice review paper on that in 2017. Many other groups around the world have published review papers on this same topic. It's really taken on a life of its own. In 2020, we published a more broad review of surface treatments for flame retardancy, not just layer by layer, but other kinds of polyelectrolyte treatments, other kinds of plasma treatments, sol gel treatments. So if you're interested in that topic, you could check out that article. In general, you can see that these 4 boxes is showing the 4 major chemistries or the 4 major types of flame retardants people play with when they're trying to protect something. Most people these days are very concerned, and I'm not a medical doctor, so I'm not saying what's true or not true, but many governments are outlawing the use of some of these brominated molecules that you're seeing here, because they've been linked to some health issues and some environmental issues. In my group, we tend to work either with inorganics like clay and or nitrogen-rich and phosphate-rich molecules. You can see some nitrogen-rich molecules there. You can see some phosphate-rich molecules here. And then hydroxides, like what are known as layered double hydroxides, and then vermiculite clay is a good example of a clay. But there's a number of different clays that are useful in flame retardancy. Before I go deep into that, I wanted to highlight a parallel technique that we do instead of layer by layer assembly, where sometimes I need 30, 40, 50 layers to get a good property. If I'm careful with how I put my positive and negatively charged ingredients together, I can make a suspension called a coacervate. It's almost like a polymer emulsion, but of like loosely bound cationic and anionic. And if one of my 2 ingredients, or if I have more ingredients, if some of them are pH responsive where they'll turn the charge off at a certain pH, you can make these stable solutions or suspensions that can be used as the starting point for a single coating system instead of a multiple layer coating system. And so let me see if I messed something up here. Okay, here it goes. Yeah. So if I use polyethylenimine as an example, you can see that at high pH, it has very effectively no charge. And then as I reduce the pH, more and more of the NH2 groups are going to become NH3 plus groups. And so its charge density increases as I reduce pH. And so I can put polyethylenimine and something called sodium hexametaphosphate, or some people call it polysodium phosphate, PSP, into a solution together. And at pH 9, it's a pretty stable suspension, and it doesn't precipitate out of solution. And then I can take cotton fabric, I can dip it into that water-based solution with those 2 ingredients. And then if I then, as a second step, dip it into this citrate buffer that's at any pH below 6, it's going to effectively ionically cure those ingredients onto the surface of that cotton fabric. And then that's very stable to even very rigorous rinsing. It's not wash durable, but you could cross-link it as a second step if that was important. But anyway, if you look at how cotton burns by itself, of course, if you touch a fire to cotton, this test that we're looking at is the ASTM D6413 vertical flame test. And if you're going to make flame retardant fabric, at least in the United States, you'll need to be able to pass this test. You can't have a char length more than 4.5 inches, I think, or it might be 6 inches. I don't know. Don't quote me. I know I'm being recorded. But anyway, that's a 12-inch panel that you're looking at of fabric, and that burning charring needs to stop well before I get to the halfway point. And that's with a 12-second propane-fed Bunsen burner flame at the bottom edge of that sample. That's how that test works. And you could see this treatment, this polyelectrolyte treatment that we put on, was able to arrest that burning process, and we protected and we passed the vertical burn test. And as I changed the pH of that second step, that citrate buffer step, as I'm lowering the pH, I'm increasing the phosphate. It's actually altering the nitrogen to phosphate ratio, and I'm getting a more favorable phosphate ratio, and I'm then getting a more favorable intumescent effect. And you can see the bottom set of images are post-burn, the top set of images are pre-burn. And by the way, you can see, much like layer by layer assembly, one of the big advantages of layer by layer assembly is that you get very conformal coatings. But this polyelectrolyte complexation that I did is also very conformal, much like the LBL process used to be. So here, and you can see evidence then at post-burn, all that bubbling is a micro-intumescent effect that's helping to shut down that fire to protect the underlying textile. Cotton, unfortunately or fortunately, is easy to flame retard. So the same treatment that I just did on cotton will not flame retard nylon and cotton together. And so we had to add an ingredient, and now it looks like I created a 3-step process, but that melamine acetate, by the way, that's a water-based solution of melamine acetate, that could be added to the PEC suspension, or it could be added to the acidic buffer, the citrate buffer. But in any event, I took that original PEC suspension, and then we added this melamine acetate. And what happens is you create melamine polyphosphate in situ, and it's a water-insoluble molecule. And that actually can flame retard the nylon part of the nylon-cotton blend. And nylon-cotton blends are very common, for example, for military fabric or for workwear, because it's comfortable and strong from the nylon. So without a coating, this is a typical military fabric for like what they call a BDU, battle dress uniform. And compared to cotton, you can see how aggressively it burns. Nylon burns much hotter than cotton. And then we dipped that same material, fabric, into a polyelectrolyte complex solution, and then into this melamine acetate, 2% water-based melamine acetate solution. It created a coating that added 19 weight% to the fabric. That's a kind of a typical, I would say, when you're making something flame retardant, that's not an unusual amount of flame retardant to add, although we have other recipes that are much lower. But anyway, this is an early example, and it worked very well. You can see we're passing the vertical flame test where we were not able to with the polyelectrolyte complex alone. And you can see with the control, what happens is you have some combination of what's called a scaffolding effect and charring, because you got the nylon and cotton side by side. You also get some melt dripping, which is bad because it spreads fire to other places. And you can see here the improvement in the char. So this is post-burn samples, SEM images, and you can see that the char is the most complete once the melamine is present. And melamine, the melamine polyphosphate acts almost like a heat sink. It actually reduces the temperature of the burning somehow during the process. We moved on from textiles more recently, and we started to look at wood. As many of you know, most of our residential buildings are made with wood in the United States, and the new kind of plywood is called oriented strand board. Some of you may have heard of OSB. And we can I'm going to do a little bit of a different treatment here. The treatment I just showed you for cotton fabric actually also works on wood, but I wanted to highlight a different chemistry for fun here. So here I made a polyelectrolyte complex with branched polyethylenimine and sodium polyborate. So boron also has the right chemical mechanisms to also help to stop fires, similar to the way phosphates work. And so in this case, that SPB and the PEI, we cured it, ionically cured it with the citric acid buffer. And then we call it treated OSB. We dip the wood into the one solution, into a second solution, and then it's treated. So it's a two-step treatment, water-based treatment. And you really can't tell the difference between a coated piece and an uncoated piece of wood at that point. And then we held a torch for 4.5 minutes. That's a weird amount of time. The reason it was 4.5 minutes is because that's how long it took for the uncoated sample to completely burn up. But the coated sample, and by the way, you can see we only added less than 6 weight% flame retardant to the coated wood. But the torch was held there for 4.5 minutes. If you flip that, I think the thickness was 1/4 inch. You couldn't tell there was any fire on the front side after 4.5 minutes. So it really did a terrific job of arresting the damage and stopping the fire from spreading on that wood. So that was pretty exciting. Similar but different is some of you may, wherever you work, you may have some involvement with 3D printing, or we call it nowadays additive manufacturing. At A&M, mechanical engineering actually has a whole room full of a whole bunch of 3D printers. And there was a fire in one of the printers and it spread to other printers, and the filament is basically fuel for fire. And the whole room was destroyed. And you can see a little newspaper article there and a link. And so we wanted to see, could we use these polyelectrolyte complexes in a completely different way? And we wanted to make it an additive to a 3D printing filament. So we took polyvinyl amine. It's a different nitrogen-rich polymer. And that same PSP I had used previously that I told you about. And then we dried a polyelectrolyte complex and made a powder, and then we mixed it into polylactic acid to make 3D printing filament. This is just the PEC that you're looking at here. And when I torch the dried PEC powder, you can see how much it intumesces when it's torched there. So this is a very intumescent additive. And so we made a filament with 25% of the complex and 75% PLA. By the way, it has all the same mechanical properties. We did DMA, dynamic mechanical analysis, and it prints the same way. We use the same printer to print pure PLA, 100% PLA, and then this 25-75 FR filament. The only maybe negative is that it has a color, but you could do things to change that if you wanted to. This is just proof of concept. That's the block T of Texas A&M. Unfortunately, because of that yellow color, it looks like Tennessee or UT Austin or something, but that was accidental, I guess I'll say. But anyway, it printed the T, and then when we put a torch on just polylactic acid, it does what we expect. It melt drips, it catches fire, it melt drips. So it does everything bad, and we don't want that. And then when I torch the 25% PEC PLA, you just into a mess. It doesn't even truly ignite. You can see the moment the torch is taken off, there's no burning, and you can keep bringing the torch back in and burning, and you don't further damage the T, in that case, the printed part. I don't have a good natural segue, but the same kind of technology can be used to make gas barrier films for food packaging or for medical packaging or other kinds of protective things, or inflatables even. One of the first things we did was we took polyethylenimine and polyacrylic acid, And those two polymers together love each other much more than they love themselves. I always say that that's rare for people and for chemicals. And in this case, like the glass transition temperature of those two polymers together is much, much higher than you would predict with the Wood equation, which is the upper bound of what you would expect the glass transition temperature to be. So we call it I didn't invent this. Somebody else, I think it's in this Progress in Polymer Science article, they termed this kind of idea a scrambled salt structure. It's two ionic molecules together, polymer. And when we did layer by layer assembly with those two polymers, an 8 bilayer coating that was about 1 micron thick had an undetectable oxygen transmission rate. So it's a pure polymer, and I can't measure oxygen going through it. Of course, oxygen is going through it, but at a very, very, very slow rate. Once I deposited 10 bilayers, and maybe that was 2 microns thick, you couldn't detect it even at 100% humidity. It was so highly ionically cross-linked, so dense. It has a modulus above 10 gigapascal as just a purely polymer thin film. So that was pretty exciting when that first came out. You can see that it was published in 2011. That was a while ago. More recently, we took those same two polymers, but we made a polyelectrolyte single solution and then just dipped a piece of PET into that solution, and then once again cured it with the citrate, just like I did with FR. It makes a 1 or 2 micron thick coating, and it's undetectable if I have the correct ratio of the two ingredients and I cure at the right pH. So that's kind of cool. So we got rid of all the processing steps and just made this really nice, clean, transparent, high barrier polymer coating. And it was so cool that we thought we should try to patent it, and we did, and it was issued, so that was terrific. You can even make an edible version of what I just told you by using chitosan and pectin instead of PEI and PAA. And exact same kind of concept. And we directly actually dipped bananas and apples into that polyelectrolyte complex. And so that was kind of fun, and, slowed the browning and slowed the oxidation. It turns out that dip coating was approximately 700 nanometers thick on both the banana and the apple. Kind of a cute demonstration there. Total left turn, even more recently, I've been doing gas barrier and fire for a long time. A government agency asked me if some of the things I was doing in those areas would have any impact on dielectric materials or high voltage insulation. And my student I didn't make this slide, I stole it from my student, but of course we know Moore's law, or many of you have heard of Moore's law about things, the size of things getting smaller and smaller. And the thing that doesn't get talked about a lot is that there's a high thermal signature with a voltage going through this very small device. And how do I protect that and keep it from shorting out and keep it insulated? And so you need thinner and thinner insulation, and you want, and of course people would like these devices to have higher and higher voltage. Well, I need to balance these things. So there's a property called dielectric breakdown strength, and you can see an example here as I'm applying a voltage to a film. Eventually, I'm going to burn a hole through that film, and then there's going to be a short if that's an insulating film, if that's a dielectric film. And so we have a test in our laboratory where we can ramp up voltage and then see at what voltage does that hole form, and then I'll get a kilovolt per millimeter dielectric breakdown strength. And so my competition, the commercial most commonly used dielectric is Kapton, or some variation of, I know there's a bunch of different versions of Kapton. But I think the breakdown strength ranges between 150 and 300 kilovolt per millimeter. Thermal conductivity, you would like thermal conductivity to be as high as possible. Most polymers have very low thermal conductivity, as does Kapton at 0.12 watt per meter Kelvin. And so there's a desire. The other thing is Kapton comes as a film, and I guess you melt it onto a surface or form it to a surface. If I could have a coating that had everything Kapton has, and I could conformally put it on any kind of a device, then that could solve some problems, I'm told. So what we did was, actually, even before we did it, a few other groups had just touched on the topic just a little bit, looking at polyelectrolytes and dielectric properties, and they saw some very interesting results. And then my group very recently got into this quite heavily and made some materials and showed some really nice properties, I think. And so I'm going to just show you one example where we took polyethylenimine and we stabilized bomite clay. That's alumina, Al2O3. It's a platelet like a clay, but it's bomite. And then vermiculite is an aluminosilicate, typical clay. That's usually a little bit anionic, but we further stabilized it with polyacrylic acid. And so we had this cationic and anionic solution, but the major component was a clay in each solution. So we were doing layer by layer with two different clay or platelet materials. So it was a unique kind of brick wall. And then we made 700 nanometer thick films that were 8 bilayers of the bomite and vermiculite, stabilized by the PEI and PEA. And so we measured thermal conductivity by doing thermal resistance with another group, Patrick Schamberger's group in the Material Science and Engineering Department. And we measured that these films had 0.16 watt per meter Kelvin, which is not great, but at least it's similar than to Kapton. So it's not terrible. It turns out PEI, PAA by itself is 0.5 watt per meter Kelvin, which is pretty high for just a pure polymer, not crystalline. So that's kind of weird, interesting. It's because it's such high density. But then if you look at the breakdown strength, so we had 0.16 watt per meter Kelvin, and we have a breakdown strength that's also very similar to Kapton on the high end of Kapton. So we have on the high end of Kapton's thermal conductivity and the high end of Kapton's breakdown strength, but this is a water-based coating technology. So that was kind of a fun thing. And so you can look, one of my student Ethan's most recent papers, you can see the in ACS Applied Engineering Materials in 2023, talks about the influence of what the platelets are doing to give us higher breakdown strength and give us a little bit of thermal conductivity. And when we measure these things at 80 degrees, we measured at room temperature and also at 80 degrees Celsius. And you can see that the properties are pretty nice. So, and this is still very early work. All our work is just in the last couple of years on this topic, and we're learning quite a bit as we're going along. So that's kind of the new, let's call it the new thing. And so anyway, I accidentally left a thermoelectric slide that I was supposed to delete. But anyway, we do a lot of other properties, same kinds of concepts, but to achieve anti-corrosion, antimicrobial, UV resistance, etc., thermoelectric. So if you're interested in any of those things, you can just look it up or you can email me. Questions that people ask me, especially industrial people: how fast can the layers be deposited if I'm doing layer by layer assembly? I would say almost instantaneously. If you look in the literature, people do 1 minute, 10 minutes per layer, and it's totally unnecessary. The layers go, whatever is going to get deposited pretty much deposits immediately. You don't have to rinse and dry between layers. Of course, you'll make a more beautiful film if you do. I have a number of things I can play with: pH concentration and speed to change layer thickness if I want to. You can laminate and seal coated PET, for example. We've done it. And you could recycle these if you took it to very high pH, for example. You could strip the coating if you wanted to off of a surface. And then flexographic printing, spraying. If you're talking about textiles, typical old-fashioned pad dry processing can be used to deposit multiple layers or even just the polyelectrolyte, one or two-step polyelectrolyte complex treatments that I showed you. So that it's a pretty, I think, feasible platform technology for putting functionality onto a surface, whether it's a textile or a film or a composite or whatever. So I won't read you the two conclusions there. So yeah, I'll open it up to questions, and I appreciate people coming to listen.
Can these coatings be applied to metals? Will the water cause corrosion under the coating?
Yeah, that's a good question. So we've actually done anti-corrosion coatings with this same technology, but you can't be careless. So yeah, you do have to be careful about what pH you're using to do the deposition. And of course, you're going to want to deposit the first layers very quickly because yeah, I don't want to be soaking metal in the water. Metal is probably one of the least things I'm coating on a regular basis, but we have done a number of different and published and patented metal treatments. But yeah, you do have to be a little more careful with metal for sure. That's a good question. But if you do it right, the adhesion is very strong. It can protect it. A nano brick wall can protect against corrosion. It's almost like a chromate replacement coating if it's done right. So yeah, I appreciate that question.
Okay, I have another question. Have you tried hybrid or hierarchical structures using nanoclays into the fiber composite structures and only on the fiber surface of the for the purpose of gas barrier properties?
Okay, I'm not sure if I fully understand the question, but so usually when people say hierarchical, they're almost saying, is the microstructure changing as a function of thickness? Like, am I getting higher modulus or lower modulus through a gradient, or something like that? I don't know if that's the question. I haven't done that, but I know people have done that. That can be done. I didn't do it. You could be changing, if you're doing layer by layer assembly, you could be changing, for example, after some number of layers, you could change the pH that you're depositing at, and it would change, for example, clay spacing, and therefore you would change the nanostructure as a function of thickness. Possibly you could do that. But I've thought about doing sizings, for example. I don't know if that, and I felt like that was another part of the question, but you could coat carbon fiber directly with this treatment technology and either put FR or gas barrier or heat shielding directly onto a carbon fiber and then put that fiber into a composite. In that case, I'd be acting like a sizing, and maybe I would have an intermediate modulus. So that could be interesting. I haven't done that. I don't know if any of that was part of the question, but that's a good question. And I haven't done any of those things that the question is asking, but it's good ideas. It's good ideas.
Okay. We have a few questions coming in.
Ooh.
Okay. Next up, I'm curious about the coating strength. Is there much testing into the wear and tear properties, and is it affected by the coating thickness?
Yeah, so I'm not a scratch guy, but my former department head in mechanical engineering, Andreas Polycarpou, asked me those same questions, and we have 2 or 3 papers published where scratch and indentation testing was done to look at the strength and the scratch resistance, and these are quite robust coatings, and they can resist scratching, and they have good modulus and good strength, surprisingly good, I would say. But I'm biased, but you can look at the papers and see what you think.
Okay, next up, with regard to the dielectric coatings, can the coating protect sharp edges and corners?
Good question. I guess it depends on how sharp, but because usually when I'm putting the coatings that I'm using for dielectric right now are usually at most a couple of microns in thickness. But yeah, I would think it's very conformal. So I guess if it depends on what kind of sharpness we're talking about, but this is a very conformal coating. So if I put it on a textile as a flame retardant, not as a dielectric, it's coating every individual 10 micron diameter fiber quite uniformly in the carb. When you look at a fabric and you see a fiber, it's actually tens of fibers that are twisted together. You can't even see the individual fibers, but this technology is coating the individual fibers you can't even see. So there's an example of a sharp, I guess you'd call it a sharp corner, sharp geometry. But yeah, so my answer, that was the long answer. Short answer, yes.
Okay, and again, another scratch question. Are your coatings self-healing, for example, from scratches?
The PEI, PEA, if you put a lot of clay in there, they become less self-healing because the clay is preventing the healing. But absolutely, we have a published paper with polyethylenimine and polyacrylic acid where we purposely scratched it, or we stretched the PET film that it was deposited on, got a bunch of mud cracking, micro cracks all over, lost its barrier, then 100% humidity for 10 minutes. It can go back in the MOCON and it has undetectable barrier again. It fully healed. Yeah, so that was kind of cool.
Very cool. We have a follow-up to the earlier question. So to clarify, instead of composite panel surface, the individual is talking about the interlaminar or intertow regions where the polymer permeability is dominant. Potential use could be linerless composite pressure vessel.
Oh, okay. Well, I don't know a lot about that, so whoever that is should contact me offline, and we could talk about doing that or something. I don't know enough about that, so I don't think I could. I still I'm not picturing the geometry in my mind. But I know I can coat fibers. I know, of course, I can coat the surface of a composite. Interlaminar, of course, you could coat a slice of something and then glue it together. So I don't know if any of that is hitting the mark, but that sounds like, yeah, that might be an offline conversation.
One more question. Excellent talk. PEI is usually branched. Would you have the same results if you use a linear?
It's a very good question, and it's actually a dumb reason why I don't use linear that much, or it's a good reason, but it's not a scientific reason. Linear polyethylenimine is more expensive, like way more expensive than branched, and it's harder to dissolve in water because I think it crystallizes, and so just because it was a pain in the butt when I was a new young professor, I never really circled back to it. But there's no good reason why I couldn't use it, so, and who knows, something could be better. It's possible. It like for the gas barrier, it might make you an even tighter network. I don't know. So that's a good question. And so the answer is no, I didn't use LPEI, linear polyethylene.
Thank you all for joining us this evening, and I would like to especially thank Dr. Grunlan for taking the time to present this.
Yes, thank you so much. And I really appreciate the questions. It was a real pleasure. So I'll catch you guys later. I feel like I need to eat supper or something now.
Well earned. All right. Well, thank you very much.
See you later.